Okay, next type of induction problem, these divisibility questions. So it's not like a series, and that's why I said to you yesterday, I don't like setting it up in the sum to k plus term k plus 1, because there is no sum here to do that with. We need a different approach. Remember, induction is an idea, but the idea of induction stays the same. We want to prove it for the first case. We will assume what it is we're trying to prove is true. Then we'll use that assumption to go and prove for the next case, and then we can tie it all together. So we need to prove n times n plus 1 times n plus 2 is always divisible by 3. And when you think about it, logically it must be. I mean, you get 3 consecutive numbers, multiply them together. Well, one of those consecutive numbers in itself must be divisible by 3. So of course this is always going to be divisible by 3. Unfortunately, that's not a proof. So let's do it. So n equals 1. Sub it in, we get 6. And yes, 6 is divisible by 3. So good, it works for the first case. It does work for the first case. Now the question is, how do we write our assumption? Right? Assume the result's true for n equals k, k some positive integer. How do we physically write it down in a form that I can substitute in? And so what I'm going to do is I'll write it as an equation. Because if it's divisible by 3, then it must be true that I could write it as 3 times something. So I'm going to say k times k plus 1 times k plus 2 is equal to 3 times something. Now that thing has to be a whole number, otherwise it's not necessarily divisible by 3. But if it's 3 times some whole number, then I know it's divisible by 3. So that's going to be my assumption. So I now want to prove the next case. So if I prove k plus 1, k plus 2, k plus 3 is also equal to 3 times some whole number. And notice you need to change the letter because clearly they won't both be equal to 3 times whatever p is. So I've changed it to q. So all I now have to do is show that k plus 1 times k plus 2 times k plus 3 I can rewrite as 3 times some integer, some whole number. Okay. So the question is, how do I get the assumption into k plus 1, k plus 2, k plus 3? And what I'll do is I'll expand it out, but not completely. In the assumption, we had k times k plus 1 times k plus 2. So I'm going to leave the k plus 1 times k plus 2 together. So the k plus 3 I will expand out. And look what happens. Expand it out, then I'll have k lots of k plus 1, k plus 2, and I'll have 3 lots of k plus 1, k plus 2. But k times k plus 1 times k plus 2, that was our assumption. So I can rewrite k plus 1, k plus 2 as 3 times p. So I now have 3 times p plus 3 times k plus 1, k plus 2. So I certainly can factorise 3, and I've now got 3 times this expression. So the only other thing I have to make sure of is this expression a whole number? Is it an integer? Now we've made a lot of assumptions along the way. We assumed p was an integer. We assumed k was an integer. So if those assumptions are right, well, if k is an integer, well, then obviously k plus 1 is, and k plus 2 is. And if I multiply an integer with an integer, so k plus 1 times k plus 2, yep, that's an integer. P we assumed is an integer. Add an integer with an integer. So yes, it's fair enough to say that this expression, p plus k plus 1, k plus 2, will always be a whole number because of our assumptions that we made along the way. So I could rewrite that as 3q, where q is p plus k plus 1, k plus 2, which we know, yeah, that will be an integer because of all the different assumptions that we made. And so there's our proof. So hence the result's true for k plus 1 if it's true for k. And since we went and proved it for 1, then it's got to be true for all the others by induction. Let's try another one. So 3 to the power of 3n plus 2 to the power of n plus 2, this time divisible by 5. This time it's not immediately obvious. Like the last one, it was obvious. We got 3 consecutive numbers. Yep, we could see that. Why is this always going to be divisible by 5? Well, let's check for the first case. We get 3 cubed plus 2 cubed. That's 35. So, yep, it does work for the first case. That's certainly divisible by 5. So my assumption, 3 to the 3k plus 2 to the k plus 2 is 5p, again where p's got to be some whole number, some integer. And I'm going to assume, prove 3 to the, well, it turned out to be 3k plus 3 when we sub in k plus 1, but 2 will be to the power of k plus 3. Again, 5 times some other integer. So I'll use q for that one. All right, so there's my left-hand side, if you like. I'm going to try this to be 5q. How do I get my assumption in? Well, what I need to do for this one is actually rearrange the assumption. I can pick either one. I've chosen the 3 to break up. In the assumption, we had 2 things. We had 3 to the power of 3k. We also had 2 to the power of k plus 2, was it? Okay. So as long as I've got one of those 2 things, I could rearrange the subject and make it the subject to the formula. So I could rearrange it. In this case, I want 3 to the power of 3k. See, I could rearrange the assumption. We said 3 to the power of 3k plus 2 to the power of k plus 2 is 5p. We're assuming that to be a true statement, so I'm allowed to play around with that statement. And I could make that statement 3 to the power of 3k is equal to 5p minus 2 to the power of k plus 2, basically moving that term with 2 to the power of k plus 2 to the other side of the assumption. And now I can sub that assumption straight in. Could have done it with the 2 if I'd preferred, because I could have rewritten 2 to the power of k plus 3 as 2 times 2 to the power of k plus 2. And then I could have made 2 to the power of k plus 2 the subject in my assumption and sub that in. Okay. So now if I expand that out, remember we're trying to show this is 5 times something. Now obviously the 27 times 5p is not going to be a problem, but I've got 27 times, or negative 27 times 2 to the power of k plus 2, and I've got 2 to the power of k plus 3. Well, I'm going to actually rewrite it anyway. I mentioned it before, I could have done it. I want to make these the same so I can factorise. So I'll change the 2 to the power of k plus 3 to be 2 times 2 to the power of k plus 2. And then I can group the 2 to the power of k plus 2's together. I've got negative 27 of them plus 2 of them, which is negative 25. And 5 will go into the 25. So now I can factorise a 5 out. And so I've got 5 times something. Is that thing an integer? And again, because of all the assumptions we've made, it's going to be fair enough because, p integer, so 27 times p, yes, that will be. 2 to the power of an integer, well, that's always going to be an integer. So, positive integer, I should say, in that case, because obviously 2 to the power of negative 1 won't be. But we assume k was a positive integer, so that's not a problem. So, yeah, it's fair enough to say, yep, that's equal to 5 times something, which does turn out to be an integer because all the different assumptions we made along the line. Yesterday, someone asked me, or a couple of people asked me, about whether we should write by assumption. And maybe this is one where perhaps I should have written to the side there, because that's maybe not immediately obvious, my assumption, because I assumed something different. So maybe to the side I could write by the assumption or something like that. And our conclusion. So since they're all true for n equals 1 and so on. Okay, we'll have a go at some of those divisibility ones. Again, there's a sheet in there if you want to have a go at those.